All right, Advanced Math 8. Here we go. We've got lesson 4.2.1, day 1. Okay, so today we're going to look at the residual plot and see if we can actually use it to help us make decisions about our least squares regression lines that we've been making. So we've already, in a previous section, learned how to graph the residual plot, which is where we just take our x values and then plot the residuals as our y values. So what we're going to do today is look a little bit more in depth into these and see if they can help us make decisions. So we start off with the problem, and this is pretty familiar to you. In lesson 4.1.1, remember that was the football one where the guy's looking through a little tube at the football game. So we're going to look at that problem and see if we can come up with a least squares regression line, because we already did a line of best fit for it. But remember, the least squares regression line is the line that is the best line possible to represent the data, because it has the least amount of residuals on it. So in order to do this, we probably need to go back to our Desmos calculator. So let's go ahead and go to Desmos. And remember, we're going to hit the plus sign, pick a table, and then we're going to put in our data. So my x's are 144, 132, 120, 108, 96, hey, it's going in order, 84, 72, 60. Okay, so Desmos sees patterns when you start typing it in. So since there's a pattern of it changing by 12 each time, it noticed what I was doing. Way to go, Desmos. That was pretty nice of you. Pretty sweet. All right, so let's put in our numbers over here, 20.7. Next one's going to be 19.6. Next one is 17.3. Next one is 16.2. And then 14.8. And then 13.1. And then 11.4. And finally 9.3. And of course, we want to double check our x and y values to make sure that they're making that I didn't type something in wrong. So 20.7, 19.6, 17.3, 16.2, 14.8, 13.1, 11.4, 9.3. Sweet, everything's going great. All right, now we're going to go into a new entry here. And remember, in order for Desmos to make a least squares regression line, we tell it that we want it to be y1, which is saying, hey, Desmos, take all of these data points right here in y1. And then we don't use the equal sign. We use the tilde sign. So there's tilde. So we want it to approximate a line, because no line's going to actually fit that data. Oh, by the way, where is my data? Hey, data, where'd you go? Let me zoom out and see if I can find my data. There it is. There's my data over there. Sweet. Okay, so there's all of our data, and it's looking pretty strong as far as its association. We've got a strong positive linear association here. All these points aren't quite an exact line, but they're pretty close to it. All right, so then we're going to do mx. Remember, we have to tell it to use these x values. So we can't just write x, we have to write x1. And then plus b, because we want a y-intercept for this one. So there we go. There is our line of best fit. Actually, it's not even a line of best fit. It's a least squares regression line. So this is the best line possible that we could come up with. So let's look at our slope and our y-intercept. So it's telling us that our slope, our m value, should be 0.13373. Let's just use 4 decimal places. So we'll call this 0.1337. And then over here, we'll call this 1.6595. Okay, so I'm going to write that down on my paper now that I have a slope and a y-intercept, and we'll come back to this in a second. So on my paper, I just found my least squares regression line. That is going to be y hat is equal to, my slope was 0.1337. There's my slope. And my y-intercept I found out was a positive 1.6595. There's my least squares regression line. Okay, next point says, what if the first data point was entered backwards? Okay, so this point up here, what if we accidentally wrote 20.7 as the x and 144 as the y? Let's go back there and see what happens. All right, so I'm going to say, okay, what if up here, instead, I'm going to hide this for right now. No, I want to hide this. Why are you being a jerk? It's not letting me hide it because it's trying to pull up. I don't want that. No. Anyways. So anyways, we're going to, stupid. No. I hate this. Oh, it's killing me. Okay, fine. Line's not there anymore. How you like that? Okay, so we're going to pretend like this one right here is 20.7. And then this point over here is 144. Where did it go? Oh, it's way up there now. Okay, so would that be considered an outlier? Yeah, it's not even close to where all the other points form. So part B says, would we consider this an outlier? Big yes for that one. That is definitely an outlier. All right, now what we want to do is see what effect the outlier has on the best line of fit. Now remember, or our least squares regression line, sorry, I get those all confused. So our line that we came up with, without this outlier in it, was 0.1337x, not 227, 337x plus 1.6595. All right, and I'm going to, red's good. Let's keep that as red. All right, so that's what our original regression line was when we didn't have this point in the wrong spot. Let's see what the outlier is doing now to my regression line. So I'm going to write the formula for a regression line. So y1 tilde mx1 plus b. Whoa! Look what the effect was. Now remember what this regression line is trying to do. It's trying to limit the distance of all of these residuals. So what happened here is when we had this outlier, the regression line was like, hey, I got to get close to this point, otherwise my residuals are going to be huge. So in order to make the residuals fit or make them smaller, it got close to this point and farther away from some of the other points. So what we have here is an outlier is going to ruin your least squares regression line. So this outlier here completely ruined my line. Look what happened. My slope became negative instead of positive. My y-intercept went up big time. It was at 1.6595 and now it's 107. So an outlier, especially a big outlier, is going to ruin your least squares line. So if you have a big outlier, number one, double check to see if you did it right or if your data is correct. And number two, consider just dropping that outlier from your data set because it doesn't fit with the rest of your data. So maybe you should ignore that outlier. Or if you're a researcher, you'd go, okay, why is this outlier here? Was there something weird that happened in my data? Blah, blah, blah. You'd go in and kind of figure it out. But for right now, we can see now that a outlier is, especially when it's way bigger than all the other numbers, it's going to ruin your line of best fit. All right. Least squares regression line. I keep on calling it line of best fit. I don't know why. Anyway, so we did that. We entered the point backwards. How does an outlier affect the least squares regression line? So we see that the outlier changes the LSRL so that it no longer models the majority of the points. Okay, let's see what I mean by the majority of the points. So the majority of the points fit with this model pretty well. This point, however, since it has a huge residual from this red line down here, the blue line, which is including that one, has to somehow limit the amount of residuals. So this blue line gets closer to limit the residuals. And now the blue line does not actually reflect what's happening with all the other points. The outlier has skewed our line so that it no longer accurately reflects the majority, because these are the majority of our points. Now with an outlier in there, the least squares regression line will no longer model the majority of their points because that outlier is throwing off. And the farther off your outlier is, the more it skews this line into a different direction. So if you've got a really big outlier, it's going to change your least squares regression line quite a bit. So usually you don't want outliers in your data. Otherwise, it's going to mess up things. All right, sketch a scatter plot of the two lines. Okay, so this can just be something really quick that we do here. So we saw the correct way that we just had a line that kind of looked like this. That was our least squares regression line. When we had the outlier, we saw that all of a sudden now the line is actually a decreasing line instead of increasing, and it's no longer reflecting what the majority of the points are saying should happen. So here we see outliers are bad news for our least squares regression line. They make our line, our model really, they make it so that it doesn't really make any sense anymore. All right, next part. Julia's father would like to open a restaurant, and he's deciding how much to charge for the toppings on pizza. He sent Julia to 8 different restaurants around town to find out how much they should charge. All right, so she goes around to these different restaurants. She looks at how many toppings they have on their pizza, and then the price they're charging for those. So statistically, how much should Julia's father charge for a 2-topping pizza? Now, he can charge whatever he wants, but if we want him to be in line with what everybody else charges, we should probably make a mathematical model to find out what a good price for a 2-topping pizza is. If only we knew how to make a mathematical model. Oh, yes, we do. We have the LSRL, the least squares residual line. So let's pull out Desmos and put in this data to see what kind of line we should have. So let's add an item, pick table, X1, Y1, that's fine. Okay, we're going to type in our toppings for X. So that'll be 1, 3, 4, 6, 3, 5, is that 0? 5, 0, 2. Okay, so 1, 3, 4, 6, 3, 5, 0, 2. Okay, so that's all working. And now the price, we got $10.50, $9, $14, $15, $12.50, $16.50, $8, and $9. Let's make sure that I typed them in correctly. 10.5, 9, 14, 15, 12.5, 16.5, 8, 9. Sweet, everything's there. Okay, so at this point, what is this yellow thing doing here? I don't know. Okay. All right, so there's our data points. Let's zoom in a little bit on them. ooh, this looks like the data is semi-linear. Yeah, pretty linear. But look at the strength of it. This is not very strong data. We've got a lot of distance in between all of these. So we don't have super strong data on this one. But sometimes you do. That's just what you had to deal with. So let's not throw a fit about it. Let's just work with what we've got. So Julia should find out what the least squares regression line is for this one. So we're going to say y1, because over here these are all y1s, is approximately mx1. So we're using the x1 over here, so that's what we're telling Desmos to do. And then plus b, because we want a linear equation. And yeah, good job, Desmos. That goes through the middle pretty well. Okay, so let's write down what we got as a slope. The slope is 1.35714. I'm just going to use 4 decimal places because that's what I decided. That's why. So it looks like she has a prediction model for a least squares regression line where the slope is 1.3571. And then the y-intercept is 7.7411. 7.7411. All right, so Julia knows math really well, making her daddy proud here. So she's going to find out how much a 2-topping pizza is. Well, toppings is my x values. So I'm going to plug 2 into here. So I'm going to do y hat equals 1.3571 times 2 plus 7.7411. So I need a calculator, so I'm going to do 1.3571 times 2 plus 7.7411 equals 10.4553. So since we're talking about money here, we should round it to the nearest hundreds. So this is going to be approximately $10.46. That's how much he should charge if he wants to be in line with what everybody else is charging. There you go, least squares regression line. So the least squares regression line, again, is the best line of fit because it has the least residuals, so the least amount of distance from your model line. And that's what you want to do. You want to limit how far away your actual points are from your predicted line. And this is the line that would model that. All right, let's go to the second page. All right, so now we really get down to something important here. We've been making lines from all this data, but not all data is going to make a line, right? Sometimes there's curves to the data. So should fitting a line to curved data, should that really make a lot of sense? No, probably doesn't make a lot of sense. So fitting lines to things that aren't lines is probably not a good idea. So how can we tell if deciding to make a line for our data was a good idea in the first place? Well, what we're going to do is we're going to look at our residual plots in order to decide if a line was a good fit for the data. Because we might get a least squares regression line, and we might say, well, this is what I got, but is that the best I could have done? Maybe a curve would have been better than making a line. So that's what we're going to look at here. So first, to get to that point, we're going to match the scatter plot to the residual plot. So here's scatter plot 1. So I see over here the residuals are really close to the line, but as I get farther and farther away, my residuals get bigger and bigger on this one. So which residual plot would that be? So at the beginning, the points are close to the line. Towards the end, the points are farthest from the line. And if you look at it, here these points are, they're close to the 0, so that's the residual. So the residuals are small here, and the residuals start getting bigger and bigger and bigger as you move away. That's what's happening here. So the residuals are getting bigger and bigger because we are getting farther and farther away from our least squares regression line at that point. So those two go together. Okay, what about this one? Well, this one, we've got some residuals spread out here. It looks like the residuals are pretty evenly spread out all across the line. So which one does that reflect? Well, here the residuals are pretty well spread out all across the line. So it looks like those two would match. Last scatter plot. I wonder which one this one's going to go with. Let's see. So what I notice here is my residuals, I got some above, some below, some above, some below, and then all of a sudden in this section, from like here to here, all the residuals are below the line. And that's what's happening here. These are all the residuals that are below the line. So we started off where the residuals were kind of, above and below. Then we got to a section of the graph where all the residuals were below the line. And then after that, we had some above and some below. So that would be this one. So scatter plot 3 goes with the residual plot A. Okay, so how do we determine if a linear model was a good idea? Well, let's just look at what we have here. So in this problem right here, scatter plot 3, look at the data. It kind of makes a curve. And so a line probably doesn't fit a curve very well. And here we see it in our residual plot. I see a bit of a pattern in my residual plot, and I don't want to see a pattern in my residual plot. A pattern means that it's not fitting the line very well. So here, this is what I want to see. I want to see randomness in my residual plot, because if it's fitting if the model is fitting the scatter plot, it means that you're going through the middle of your data, and some points are going to be above and some points are going to be below. And it should be spread out. You shouldn't see a pattern. So this one right here, that's pretty good. This means a linear model was a good fit. Now this one over here, there's a bit of a pattern to this data. It looks pretty close, but then it just spreads out all of a sudden. That's a pattern. So we see this pattern happening here. That means a linear model is not a good fit. So these two are telling me, by looking at the residuals, since I have a pattern in my residual plot, that means probably shouldn't have made this into a line. Maybe there's a different type of equation other than linear equations that would better fit my data. And that's what the residual is telling us. Since there's a pattern in the residual, it's telling me, you know what? You probably shouldn't have used a linear equation. There's other equations out there in the world. Maybe you should have used one of those to model your data from. Whereas this one over here is saying, yeah, everything's nice and spread out. There's no pattern here. So yes, linear model probably was a good equation or a good type of equation to use for this type of data. Okay, a curve or quadratic or an exponential, those probably wouldn't be good models. A linear model is probably the best one because your residual plot is not showing a pattern. Here, your residual plot is showing a pattern. The farther you go away on the x-axis, the bigger your residuals are getting. That's a pattern. You don't want to see patterns in your residual plot. If you see a pattern, it means a linear model was probably not a good fit for your data. So which of the scatter plots does a linear model fit the data best for scatter plot 2? And what we're looking for is if the linear model is a good fit, then the residual plot will not reveal a pattern. This one, there's no pattern to our residual plot, so that means a linear model was a good fit for that data. All right, that's all I got. Be good. Math hard. See you later.